So I'm planning to talk about exercise 2. So the sample mean, x bar, is a good estimator of the population mean. It can also be used to predict a future value of x, and independently. Okay, so there's a keywords here that we might use later in the procedure. So independence. Okay, yeah, and it's used for prediction. Assume that you have a sample mean x bar and a sample variance s squared, and then based on a random samples of n measurement from a normal population. Okay, so x bar and the sample variance are based on the n observations from a normal population. So our task is that we construct a prediction interval for new observation, let's say x0, and then using the 1 minus alpha confidence level. Yeah. So the hints here is that we start with the x bar minus x0 minus x bar, and then use the t distribution. Yeah. So yeah. So let's construct the confidence interval. So yeah, maybe the hints is not too straight. Actually, just referring to the hint, instead of x0 minus x bar, maybe it's more either way. So x0 here is defined as your new observations, and then we want to predict a confidence interval for this new observations. And we want to doing that by using the confidence interval for x0 minus x bar, and that is coming from the hint. Okay. So yeah, although the question did not specify explicitly, here we just write down more explicitly regarding the distribution for the observation. So this is for the observation, and this is the x0 is the new one. So here I is, let's just distinguish them, I is from 1 to, let's say, smaller case n, not the 0. So 0 is referring to the new observation. Okay, so this part is referring to the question that is based on the random samples of n measurement from a normal population, but it does not specify mu and sigma. So here we just assume that it's mu and sigma because it's not given in the question. But here, this is what the question is referring. Okay, so first of all, we need to find the maybe let me ask a question. So what would be the distribution for new observation x0 minus x bar here, where x0 is also coming from this distribution? So what would be the distribution of this difference here? So this is just a normal random variable minus another normal random variable, so it should also be a normal distribution, right? Okay, so that's the first thing. And next we just need to solve for the expected value and then the variance, and then from there we can construct a confidence interval for this difference. So that will be our strategy here. Okay, so next we just need to solve for the expected value first. So what would be the expected value for this x0 minus x bar? So I'm not sure how detailed that is required, but so the expected value for this x bar, for this new observation, should be mu, and then the expected value for the x bar, which is the average of the samples that is also coming from this normal distribution, is also going to be mu. So this is going to be a 0. So the difference between the new observation and the sample mean will be 0. So maybe I can also write down the distribution for x bar, which is mu and then the sigma square over n. I think you should already be very familiar with all these parts. Yeah. Any question up to this point? Okay, so what we are interested in is the difference or the confidence interval, but the bottom line is that we need the distribution. So we recognize that this is going to be a normal distribution, and we also recognize, the mean is going to be 0. So the next step is to find the variance, which is the third component that we need here, okay, which is the variance of x0 minus x bar. Okay, so what will be the variance of this difference here? Any thoughts or comments? Yeah, so it should be the variance of the individuals, and then this should be a plus for when you need to square the -1 from here, so it's a plus, and then the variance of x bar, and then minus 2 times the covariance of x0 and then x bar. Okay, so here we need to use the information that we point out earlier, because this new or a future value of x, or the prediction, is independent of the select of the data point from the observations. So this will becomes 0. So this is due to the independent. The new predicted value is independent to the observed data. So then the covariance just reduced to 0. So this is referring to this one here, that we highlight the keywords independent here. Okay, so next we just need to calculate the variance of x0 and then the x bar. And then from here, we already know that the variance of x bar is just the sigma square over n. And this should be sigma square, since the new prediction or the new data point, although it's unknown, is also coming from this distribution here. Yeah, and we can further write this as 1 plus 1 over n multiplied by sigma square. Okay, so we also have the information here, which is sigma square 1 plus 1 over n. Okay. So any question up to this point? Okay, so let me just summarize a little bit. The question is that, or what we want is the confidence interval for, let's write down confidence interval for x0. In order to get that, we first, or from the hint, we need the distribution for the difference of x0 minus x bar. Okay, so we need the distribution of that. And then we comment on the distribution. So first of all, we recognize that this is a normal, because this is a normal random variable minus another random variable, and it should also follow a normal. Okay, so we have that, the distribution settled. And next, we just need to find the expected value and the variance here. And as we expanding here, the expected value for the difference is going to be a 0, and then the variance of the difference is going to be that. And this is another information that the distribution for x bar is also normal with this mean and the variance. Yeah, so that is what we have been doing so far. Okay, so once we have the distribution of the difference, now we can start to think about how we can construct the confidence interval. So first of all, we need to standardize this general normal. We can do so by centering the mean, which is the 0 of this distribution. So we just need to minus a 0 here, and then we need to divide it by sigma of 1 plus 1 over n. So divided by the standard deviation. So this is a general normal distribution, and then here we standardize it to convert into a standard normal random variable. Okay, that's that. But the question here, or the problem here, is that we don't know what is the sigma. So sigma is unknown. So we need to, say, using data to estimate this variance to further facilitate how to construct this interval. So another information that we're going to use is that n minus 1 multiplied by the sample variance over the population variance. This is following a chi-square distribution with degree of freedom n minus 1. Okay, so this is another information that we can use. Okay, and then we can construct a following statistic, which is let's denote it as t. And then we have the standard normal on the numerator. 1 plus 1 over n square root. Okay, and then divided by a chi-square parameter, s square over sigma square, divided by its own degree of freedom, and then taking the square root. So what we have here is a standard normal random variable over a chi-square random variable with degree of freedom, let's say here I'm just referring to a general case, divided by df. And this should give you a statistic, and here we denote as t, that follow a t distribution with degree of freedom n minus 1. Yeah. Okay. So here, just to summarize why we need to do this, is that we want to construct the confidence interval. And then we know that this is going to be a normal. But because the sigma is unknown, so we need to introduce additional information to further construct the interval. And the information that we introduce is this chi-square distribution. And then by using the z, the standard normal, divided by chi-square, divided by degree of freedom square root, and then we can construct another random variable. And this random variable, by definition, is going to follow a t distribution. Yeah. And then from this ratio, if you simplify the form, this will also be equal to x0 minus x bar over the sample variance s and the 1 plus 1 over n. Okay, so as you can see that this one has nothing or does not involve the sigma, which is unknown. It only requires x bar and s square, and both of them can be calculated from data. Okay, so everything except the variables of interest, x0, and for the remaining components, they can all be estimated or evaluated if you have n measurements from the distribution. So with that, and we also know that follow a t distribution, then we are able to construct a confidence interval for x0. So we can write it, so now just to write down the conclusion. So the probability for, let me just write from the left-hand side. So alpha over 2 n minus 1. So for this random variable between this quantile, over 1 plus 1 over n less than the positive alpha over 2, 1 minus n minus 1. Okay, so this particular event has a probability of 1 minus alpha. and then you can just move around the terms in between, inside the parenthesis, and then you will get the confidence interval. So x0 is the confidence interval for that is x bar plus and minus the quantile for t from the t distribution multiply. So this is multiplied by the standard error. So this can be calculated from data. This you can use the say either computer software or the table to find this quantile. S can be found from the data, and then the n is already known. So everything on the right hand side is given or can be calculated. Then you have a prediction interval. Let me use the words from the question. Prediction interval, yeah. So this is called a prediction interval. For a new observation that you want to predict x0. Okay, so any question or comments on this part? Okay, then let's talk about question 4. I think this is very similar to what we have seen from maybe previous homework. So we have x1 to xn and then y1 to y12. They are two independent. Okay, so again, keywords independent. So we will for sure that going to use some information about the independency here. And then they are coming from the respective normal distribution, mu1 sigma 1, mu2 sigma 2. And we also have additional information about sigma 1 squared is 3 times the sigma 2 squared. Define a random variable that has a t distribution and use it to find a confidence interval for mu1 minus mu2. Okay. So yeah. Here we are asked for a random variable that follows t distribution, so we are going to use the similar definition for the z over chi-squared divided by degree of freedom to construct that, and hopefully that can serve as a confidence interval for mu1 minus mu2. Okay, so this is for question 4. So the things that are one, say, intuitive estimator we can start with is x bar minus y bar, and then hopefully this will have some connection with the interval of interest y1 mu1 minus mu2. So we want a confidence interval for mu1 minus mu2. Okay, so we can start from so yeah, just coming from the intuition that usually x bar is a good estimation for mu1, and then y bar is a good estimator for mu2. So hopefully that this difference of x bar minus y bar can serve as some, or can give us some distributional information regarding that. Yeah. So that's the reason why we want to start with x bar minus y bar. Okay. So each of the xi following a normal will mu1 sigma 1, and then yi following a mu of mu2 sigma 2. Yeah, so here we have the difference of a two normal random variable. So again, this difference is going to follow a normal. Then the question is what will be the mean and the variance for this difference here. So intuitively that the difference for the mean for this difference is mu1 and mu2. So as you can see, evaluating the distribution for y bar minus x bar minus y bar, it should give us some information about mu1 and mu1 minus mu2. That should answer the question. And then the question is, what would be the variance for this difference? So yeah, you can also use the similar, so well, I'm not going to provide, well, I think I provided this in the previous question before, but I'm just not going to do it here. So the difference, so the variance of this difference should be mu1 squared over n1 and then mu2 squared over n2. Okay, so maybe just write down this. I think I showed this one when we work at some previous homework problems. Okay, so that is the variance of this difference. But any question regarding the up to this point? So again, it's the same three components. One is the distribution for this difference, and then what is the expected value for this difference, and then what is the variance for this difference. And then later we will use this normal or this distribution to calculate a confidence interval for mu1 minus mu2. So up to here, we already see that it has some connection with mu1 and mu2. We just need to elaborate that a little bit. Okay, so we also have another information that is regarding, where is it? Okay, yeah, sigma 1 squared is 3 copies of sigma 2 squared. So let's see what we can rewrite here. Then maybe we just write the... Okay, so now let's just plug in. So sigma 1 squared is just 3 copies of sigma 2 squared. And then n1, okay, let's write down n1 is, from the question, is 9 and n2 is 12. Okay, so n1 is 9 and then n2 is 12. Okay, so now let's just plug in the numbers here. So this is 3 copies of sigma 2 squared over 9 plus 1 copy of sigma squared over 12. Okay, so yeah, so that will be the distribution. But again, also coming from the question, sigma 2 squared is unknown. So we also need to use some distribution regarding the sample variance. Well, we already see is that n minus 1 squared over sigma squared, following a chi-square of n minus 1. So for sure, in this question, we also need to use this information to calculate the confidence interval. Okay, so first of all, let's define the standard normal, which is x bar minus y bar. And then you need to center around to 0. So you need to minus mu1 minus mu2. And then standardize it by its standard deviation. So 3 copies of sigma 2 squared over 9 plus 1 copy of sigma 2 squared over 12. And then taking the square root. So this is the standardization from a general normal to a standard normal. Okay. So again, sigma 2 squared is unknown, so we also need to use that. So we also need to construct a chi-square distribution. Yeah, so by doing that, our goal, or our intermediate goal, is that we want to cancel out the sigma square, so that, similar to the first question, that the confidence interval can be constructed or can be evaluated by all the components from everything that we can evaluate from the data. Yeah, so we need to construct the chi-square in the following way. So n1 minus 1 multiplied by s1 squared over sigma 1 squared. So if we directly using this chi-square in the denominator, we are not able to cancel out the sigma 2 squared. So that means this chi-square is not enough to construct the confidence interval that we intended. So we need additional copy, which is the n2 minus 1 multiplied by s2 squared over sigma 2 squared. And this also follow a chi-square distribution of n2 minus 1. So this is n1 minus 1. Okay, so if we use either of them, we are, let me think about it. Well, okay, either way, we are just going to use the sum of these two chi-square. So again, there's also another independency here, because the data point from the first group, x1, so the x is referring to one group and the y is referring to the other group, and then they are independent of each other. So that's why the sum of two independent chi-square is also going to be another chi-square distribution. So this is n1 plus n2 minus 2. And this is just the 9 minus 1 multiplied by s1 squared over sigma 1 squared plus 12 minus 1 s2 squared sigma 2 squared. And this can be further simplified to 1 over 3 multiplied by 8 multiplied by s1 squared plus 11 multiplied by s2 squared over sigma 2 squared. Okay, yeah, so this is just to simplify the numbers, and then also by replacing one copy of sigma 1 square is 3 copies of sigma 2 squares. So with that, and then you will end up with this, and this is following a chi-square distribution with n1 plus n2 minus 2. Okay, so now we have one copy of a standard normal and then one copy of a chi-square, and then we are ready to construct the t and then to get the confidence interval. So we are going to construct a t statistic in the following way. So first of all is the standard normal on the numerator. So x bar minus y bar minus mu1 minus mu2 over, let's see if we can further simplify that. So here I'm just going to group it in the one over 3 plus 1 over 12, and then taking the square root. So I'm just grouping the denominator here to write it in a more, say, compact form. So we have the standard normal on the numerator, and then we need the chi-square for the denominator. So this is the 1 over 3 multiplied by 8 multiplied by s1 squared plus 11 multiplied by s2 squared over sigma 2 squared, altogether divided by 19, which is the 9 plus 12 minus 2. Okay, so from here we are able to cancel out the sigma 2 squared here, and then leaving all the components remaining can be evaluated from the data. So that would be the reason. And this can be simplified to x bar minus y bar minus mu1 minus mu2 over 1/3 multiplied by 8 s1 square plus 11 multiplied by s2 square. And there's also a constant term, so 228 over 5. So if you calculate it or simplify this form, you will end up with this. Okay, and this is following a t distribution with degree of freedom 19. Okay, so any question up to this point, just for how to construct the t distribution? Yeah.
You said we don't want sigma not to show it.
Yes, that would be the reason why we need to take this division. So as you can see here, there's no sigma 2 or sigma 1 involving. So this can be estimated by data by taking a sample average of the 9 observation. This can be taking the average of the 12 observations. This can be calculated by summation xi minus x bar square over n minus 1, similar for the y. So everything you can calculate from here. Yeah, that follow a t distribution. And then we can construct that. So again, you can similar here. You have the things that you constructed in the middle. They are in between the two quantiles of the two t distribution. So that from here, mu1 minus mu2 is in the interval of x bar minus y bar, and then plus and minus the t of alpha over 2 n minus 1. So this is the quantile from the t distribution multiplied by the standard deviation, standard error. So the standard error is the 228 over 5 square root of that 1/3 multiplied by 8 multiplied by s1 square plus 11 s2 square. So again, as you can see, the things, everything on the right hand side does not involving anything we don't know. So x bar can be estimated, y bar can be estimated. This can be found from the table or computer software. This is a constant. Mu1, s1 and s2, they're all known. So you are able to say like mu1 minus mu2, let's say is in 128 to 356. So something you can calculate it explicitly. If it involving sigma 1, mu sigma 2, we don't know what that number is. So we are not able to come up with the number. And then we cannot have the interval. So that would be the most important reason why we need to using this kind of like a relatively complex ways to manipulate, divide it, multiply lots of things to finally come up with this complex expression. The goal is to cancel out the sigma 1 and sigma 2, which is what we unknown. Yeah, that would be the underlying reason. Yeah. So if you have data and then you can plug in and then you can calculate explicit number, and then you can tell people that the confidence interval for mu1 minus mu2 is between these two numbers. Yeah. If you don't do this long division, then you cannot come up with particular numbers. Yeah. So then you cannot, that's not the confidence interval. Yeah. Yeah. Any question or comments? Okay, then maybe let's talk about exercise 5. I'm not sure if we still have enough time. So exercise 5a, okay. So x1 to xn independent. Okay, again IID. So we're going to use it somewhere in our calculation, and then each of them follow a normal mu and sigma. Suppose sigma square is known here, and then using the definition of sufficiency to show that x bar, which is the sample average, is a sufficient statistic for mu. So the definition for the sufficiency, or to show that the sufficiency is that the conditional PDF of x, and then given the estimator, so that conditional PDF does not involving mu, and then we can claim that this sufficient statistic t, this estimator t, is a sufficient statistic for mu. So that would be the strategy here. But this is just coming from the definition of the sufficiency. Okay. So let's write down say mathematically on what does that mean. So 5a. So x1 to xn follow, IID, normal, mu, and the sigma. And then the PDF for x1 to xn with parameter mu and the sigma square is just the product of the normal, because they're IID. So the joint distribution is going to be 2 pi sigma square and then negative n over 2. So for one observation it's 1 over 2, but here we're taking the product, it's n over 2. And then the exponential of negative 1 over 2 and over sigma square multiplied by summation of xi minus mu. So this is from 1 to n square. Yeah. So this is just the products of from 1 to n f of xi. Yeah. So if you taking the product and then this one, that one will become an n, and instead of one copy you will have need to do the summation. The reason is that the product of the exponential is the exponential of sum, so you have a summation here. Okay, so that is the joint PDF. But we are interested, but to evaluate the sufficiency based on the definition, we need to calculate the conditional PDF, and that is given on the estimator. So our estimator is y bar. And then also from the previous two exercise, we know we already seen this. So this is just centering on mu and the sigma square over n, which is also a normal distribution. So we know it's normal, we know it's centered around mu, and then we also know the variance stat. So we can also write the f of x bar, which is also parameterized by mu and the sigma square. It's having the following distribution formulation. So again, 2 pi and sigma square over n. So 2 pi variance. That's that. And here we only have one copy, so 1 over 2. Square root, yeah, okay. And then the exponential of negative 1 over 2 times the variance, so sigma square over n. And then times the x bar minus the mean, which is the mu in this case, square of that. Okay, so we have the distribution, the joint distribution for x1 to xn. We also have the distribution for our estimator. So now we need to find the conditional distribution of x1 of xn given x bar. And this is defined as the joint of x1 of xn over the distribution of x bar. So here I'm just not going to write down the mu and the sigma anymore here. Okay, So that would be the conditional PDF of x1 to xn given t of x. The t of x in our case is just the x bar, our estimator here. Okay, so now it just, again, plug in the corresponding, so this equation divided by this equation. Let's see what are some good ways we can simplify. So 2 pi sigma square negative n over 2 over 2 pi sigma square over n negative 1 over 2. So that's the constant part. And then the division of exponential is the exponential of difference. So this should be, okay, maybe we'll keep it as the exponential form. Maybe that would be easier. So exp of negative 1 over 2 sigma square summation xi minus mu square over exp of negative 1 over 2 sigma square over n x bar minus mu square. Okay, yeah, so our goal next is just to keep simplifying this division. Maybe I'll just using the space here. So that conditional can be simplified to okay, so maybe let's just make comments here, and then I'll continue that. Maybe this will help you on simplifying this division. So one thing we can do is, so here we're just focusing on this one. We need to expand or manipulate this part here a little bit, and then that will help you to cancel out with this term in the denominator, but it needs some manipulation here. So 1 over n, summation from 1 to n, xi minus mu, which is this term here, can be elaborated or can be manipulated in the following way. So let's do plus and minus x bar. So this does not alter the quantity here. We just add and minus the same form. This should give you summation of xi minus x bar, xi minus x bar plus x bar minus mu altogether square. This should be a summation of xi minus x bar square plus 2 copy of xi minus x bar minus mu, and then plus x bar minus mu square. And the summation here is referring to this entire expression. Okay, so the next thing is that we distribute the summation. So we have the summation of xi minus x bar squared. And then we have 2 times x bar minus mu. So this serves as a constant, but the summation is going to affect on the xi minus mu because you have an index I here. And then plus the summation of the third term. This third term is a constant, so just n copy of that. So you just sum over n identity copies, so you just have n multiplied by this difference. Okay. Oh, I see it. No wonder there's a typo here. No wonder I'm confused. I copied the wrong terms. So the summation is xi minus y x bar. Okay, yeah, here. I copied the wrong term. So this is a constant. So 2 multiplied by the constant, and the summation only affecting on this one. Yeah. So this is xi minus x bar. Okay. And here you can already see that this part is similar to something in the denominator here. So later it will be helpful to cancel out with this part in the denominator. Another information is that 1 to n xi minus x bar is equal to 0. Does that make sense to everyone, or if we need to elaborate a little bit here? So yeah, you can plug in this one here into the x bar, and then expanding this, and then you will find it is equal to 0. Okay, so that's another information or another comment here. So that means this thing will reduce to 0, and then you will have the summation 1 to n xi minus x bar squared plus n copies of x bar minus mu squared. So this, again, just to summarize, this is referring to some manipulation of this term here on the numerator here. We are going to expanding this in these ways. The reason is that we want to cancel out with, or we want to ease our computation on simplify this margin or this conditional distribution. Okay, so now let's plug in. Okay, we only have 2 minutes, so yeah. So if you plug in this one, so you will notice that there's a constant n in the front, but don't forget there's also a n here in the denominator for this distribution here. So when you plug in this form to replacing this part on the numerator and then simplify with this ratio, in the end you will get the conditional PDF equal to, here I'm just going to write down the answer. You can simplify on your own and then see if it's matching. So negative n over 2 over sigma over square root of n 2 pi. Okay, so the constant term remain the same. So this fraction in the front remain the same. And then multiply by the exponential of 1 over 2 sigma squared summation of xi minus x bar. Okay, so as you can see, only involving this one here. So the second term, let's say the one that I circled here, when you plug in, it will cancel out with this one here. So only resulting the summation of xi minus x bar, which is coming from here. And in the end, the conditional PDF not involve mu. Okay, so just by looking at this, there's no mu showing up anymore. And then we can conclude that x bar is a sufficient statistic for mu. Okay, yeah, so that should be our conclusion for, or that should solve 5A. Yeah. But the high level idea is that the joint over the marginal, we have the conditional. And after the simplifying the forms using some tricks here, the conditional PDF not involving mu. And then we can claim that the T of x, which is x bar, our statistic, is a sufficient statistic for our parameter mu here. Okay, yeah, thanks.